Okay, now we're going to continue going through forms of energies. And we're going to focus right now on internal energy. You're like, wait a minute, wasn't that just you? Yes, it is you, but it's still helpful for us to talk about some things. Okay, now here are some various forms of internal energy. And it can come from all of these things. I mentioned translation, rotation, vibration. There's also electronic transitions. I have electrons. If they go up to a higher level, that's a form of energy. The electrons spin, then there's a nuclear spin. All of these things are things that can happen inside of your atom. And they're all the things that we just sum up together to make you as a function of temperature. Now, of all of this, there is first sensible energy. That's the portion of the internal energy that's associated with the kinetic energies of the molecules. So technically, that's these three right here. That's really what goes into you. The other ones, they are connected to it, but not as clearly. Then I have latent energy. This one is important once we get to chapter 3 because it's all about how if I go from a liquid to a gas, it takes energy just to do that. Even if they're the same temperature, it takes energy from water to go from liquid to a gas. And until it goes from gas to a liquid, that energy is not released. That's actually how your refrigerator works. It works by stealing energy by turning into a gas and then releasing that energy by going into a liquid. So in the cold spot, it goes to a gas and it steals energy. And the hot area outside of the fridge, it releases it. And that's how your fridge works. Magic. All thanks to latent energy. Then I've got chemical energy, which we will be talking about as we start going into chemistry. That's mostly in applied thermodynamics and also propulsion. Because if I have heat going into a system, a lot of times we'll write things like this, like a flow going in one side, going out the other, and there's heat going into it. The heat's just not magically there. I'm not just like, I don't go to a heat store and buy heat. No, I burn something typically. So that's like a piece of coal or gas or some sort of fuel that's being burned, and that's where I get my heat from. And where does that come from? Chemical energy. And we can figure out exactly how much energy that is. And finally, nuclear energy, which we're not going to talk about at all in this course or the next one. And that's just talking about how atoms hold together. There's a massive amount of energy there. Nuclear energy is very, very important and it powers a whole lot of homes. But for us, we're not going to be dealing with that. That's outside the realm of this course. Okay, so like I said, our thermal energy, which is thermodynamics, thermal, is our sensible plus latent. Our internal energy is everything, okay? Everything. And so the internal energy of a system is simply all of the microscopic energies. I promise there'll be no explosions in this class, at least not nuclear explosions, maybe other ones. And so that's what we're going to be dealing with here. We have to figure out how all of these change. Now, nuclear energy, it really doesn't change much for us, but sensible and latent energy definitely does, and chemical energy later on will most definitely be changing. Okay. Now, the total energy of a system, it can be viewed as static, as in it doesn't change. But we can also have dynamic forms of energy that are changing, that are transferring from one to another, and these energy interactions. Now, dynamic forms of energy, this guy right here, are recognized when we have a system boundary. So at a boundary to a system, let's say I have, let's make a pot. You're cooking something, and this right here is my boundary. I've got a pot. It's got water in it. And there are two ways that I can do something to that water and increase the energy of the system. I can turn on the burner. If I do, it will heat up because it's putting heat into it. We see the heat, this dynamic form of energy, because it crosses that boundary. It moves from one place to another. Another thing I could do is I could put a lid on it. And technically that's not really doing too much, but it is applying a pressure. And because it's applying a pressure, I could consider that to be sort of work. And so that's another way that I can actually interact with a closed system. I can apply work to it. I can also apply heat into it. That crosses the boundary, even if no material is leaving the system. Now, what is the difference between heat transfer and work? If temperature is what's driving everything, then it's heat transfer. Otherwise, it's work. If you're pushing on it, pulling on it, spinning it, stirring it, expanding it or contracting it, and you're having to do that by hand or with some sort of machine, it's work. Otherwise, if you're just heating it up because you're burning something, if it's cooling down because it's giving off heat, If you say the word heat while you're talking about it, it's heat transfer. So heat transfer is temperature. Otherwise, you can just call it work. And that's going to be a catch-all for us, because this could be shaft work, like you're spinning something. It could be the expansion of a cylinder, like you have a piston that's moving. There's all kinds of different works. That could be spinning a wheel or spinning some sort of other device to make power and electricity. All of those could be work. Okay, they're all work. They're all fine ways of doing it. So, a bunch of different ways of doing it here. Okay. Now let's talk about macroscopic kinetic energy versus microscopic kinetic energy. Now, if I look at this water wheel right here and it's inside of the water, that water has kinetic energy. We don't necessarily see it. Like if the water was perfectly still, it might look to us from the surface the water's not moving. If you go into a pond and the pond is just nice and still, it looks like it's not moving, but that's not 100% true. The water molecules, if we moved in a microscopic view, they're moving like crazy. They're bouncing around just like in this picture. The thing is that microscopic kinetic energy is random. It's completely random. Each of these guys is bouncing around in different directions. And because they're all bouncing around in different directions, this water wheel will not turn, because all those random interactions are canceling each other out. Some go left, some go right. Others go up, others go down, and it all cancels out to do nothing. Now, if we want to do something useful with it, we have to transform that microscopic kinetic energy into macroscopic form, which means it has to be directed. So in this case, I take all of that microscopic kinetic energy, I direct it along a single path. I'm doing this through a pressure gradient. I've got pressure up here from the weight of the water, and it pushes it out here because there's less pressure. And that will cause this to spin. So one thing we care about in this class is figuring out how can we transfer this microscopic form of energy into a macroscopic useful form. Because if I don't know how to do that, then why am I heating something up in the first place? And applied thermal is going to be really focusing on that a lot for different cycles and systems. Aero will go into different types of engines and jets and propulsion devices that will be using it. So we're always trying to figure out how we can turn that heat into something useful. And remember, the random kinetic motion, that's related to temperature. So the faster they bounce, that means my temperature is higher. The slower they bounce, that means my temperature is lower. So the more microscopic kinetic energy I have, the higher my temperature will be, and vice versa. Okay, got an example, so we'll start this next time. Thank you all for listening. I look forward to seeing you next time. Bye-bye.